Okay, so we're actually going to move into the next chapter, which is about probability. Combinatorics and probability are very closely related because in order to do probability, you still need to find how many ways something can occur, which came from the combinatorics part. And we're going to be matching that over the next few lessons here. But today's lesson is just about probability and an introduction to it. So what is probability? Well, it assigns a number between 0 and 1 to an event as a means of indicating the likelihood of the occurrence of that event. Obviously, the number that is closer to 0 is less likely to occur, and a number closer to 1 is more likely to occur. The other vocab word that we really need to know from today is called sample space. This is a set of all possible outcomes in the experiment. So probability in a nutshell is the number of ways the desired outcome can occur over the number of possible outcomes, or the sample space. Okay, so this first example here, just identifying what probability would look like. Okay, suppose a standard six-sided die is rolled, give a sample space for this experiment, then find the probability of rolling a prime number. So very first, for sample space, okay, if we go back up to the definition, it is a set. All right, so that means it involves brackets or braces. Okay, so all the possible outcomes of rolling a standard die would just be 1 through 6. Okay, for you to actually find the probability of rolling a prime. Okay, now this is how this is written. This means probability of your desired outcome, the event, whatever it is that you want. All right. Again, probably easiest to write these as a fraction. The number of possible outcomes in this case would be how many elements are in the sample space, 6. And then of those elements that are prime, that actually fit the condition we're talking about, 1 is not prime, but 2 is prime, 3 is prime, and 5 is prime. So you've got 3 successes over 6 possibles. So the probability would be 3 and 6, which we would reduce to 1/2, or 0.5. Because again, this number is between 0 and 1. Okay. All right, when we are dealing with multiple events, okay, typically we're just going to start with 2 events, either one occurring. So the probability of A or B happening, all right, is equal to the probability of A happening plus the probability of B happening, and then you also have to minus any overlap between A and B. Okay, so let's say again with that die example, if you wanted the probability of prime or odd, okay, well that would be the probability of getting a prime number plus the probability of getting an odd number, but then you have to consider their overlap. So you'd actually subtract the probability of getting any prime and odd numbers. Okay, does that make sense? So this just, at the end here, this just means make sure you don't count things twice. Okay, and that brings up something called mutually exclusive events. Mutually exclusive events, events that cannot occur at the same time. So it can be kind of confusing here. Okay, listen, mutually exclusive events. Okay, 2 events are mutually exclusive when they can't happen at the same time. Okay, so building off of that, the event not A, so whatever A is, this would be everything but what that is. Okay, denoted A bar in this text, it's A bar, occurs when A does not. Okay, since A and A bar are mutually exclusive and one or the other is certain to occur, okay, let's just think about it. Okay, you either have a prime or a not prime number. Those are the only two outcomes you could get. Okay. So then the probability of not A occurring is equal to 1 minus the probability of A occurring. And these are interchangeable. Okay, these two could be exchanged easily. So just keep that in mind when you're doing some of those problems. It's much easier to simply figure out the probability that A could occur and then subtract that from 1 to figure out the probability that not A occurs. Okay, let's look at it. A standard deck of playing cards consists of 52 cards, with each suit, which are hearts, diamonds, spades, and clubs, consisting of 13 numbered cards, ace through king. If the deck is shuffled, what is the probability that the top card is a black ace? Okay, so again, we would specify probability of a black ace is equal to, well, it tells us the sample space is 52 cards. So right away we know that this is out of 52. The number of black aces in the deck, we have to kind of know a little bit about a deck of cards here. Okay, you've got two suits that are red, and those are hearts and diamonds. And then you have two suits that are black, spades and clubs. So there's one ace that's in spades and one ace that's in clubs. So there are two successful elements that meet this criteria. So 2 out of 52, and again, you would probably reduce that to 1 out of 26. Okay. Not a club. The probability that you draw not a club. So you could write something like that. Okay. Well, kind of an easy example in this regard here, right? If each, well, okay, there are 52 cards. Each suit has 13 cards. Okay, so that means there's 13 hearts, diamonds, and spades, and clubs. Okay, but we want not clubs, so we want these three groups here. So 3 times 13 is 39. 39 out of 52 actually reduces to 3 out of 4, which, again, if you didn't think of it in terms of, the 39 out of 52, you have 4 suits, you want one of the other 3. Okay. And finally, a diamond face card. So a diamond, that's, that's a really good diamond. Pretend that's a diamond. Okay, so a diamond face card. Well, for the definitions of a face card is any card that has a face on it. So we're talking jacks, queens, and kings. Okay, those are the 3 face cards. Since they have to be specifically diamond, it's only the jack of diamonds, the queen of diamonds, and the king of diamonds. So there's only 3 diamond face cards out of that 52. And that does not reduce, so you would leave it as 3/52. All right, 2 more problems. Suppose a red die and a white die are rolled. Think of them as both standard dies. Okay, what is the probability that the sum of the numbers showing on the dice is 9 or 10? Okay, again, think of how you can roll a 9 with 2 dice. Okay, and it's important, you've got 2 different die here. One's red and one's white. So think about it. If you roll a 6 with the red die and a 3 with the white die, that makes 9. But that's different than if you rolled a 3 with the red die and a 6 with the white die. Okay, so there's 2 different ways you could roll a 9. Okay, you could also roll a 4 and a 5, or a 5 and a 4. Okay, Those would be all the ways that you can roll a 9 with 2 dice. Okay, so there are 4 ways. Okay, when it comes to the 10, you have to either roll a 6 and a 4, or a 4 and a 6. But then you can also roll a 5 and a 5. Now this one doesn't have a double because 5 red and 5 white is the same as 5 red and 5 white. Okay, it's the same thing. So there are only 3 ways to get a 10. Okay, so when we're finding the probability of 9 or 10, remember it's the probability of 9 plus the probability of 10. And these are mutually exclusive. You can't roll the dice once and have both a 9 and a 10. Okay, you can't have that. So you wouldn't need to subtract anything at the end here. So this would just be 4 out of 36 plus 3 out of 36. Now, where did I get the 36 from? Well, there's 36 outcomes when you roll 2 dice. 6 outcomes from the first, 6 outcomes from the second. Fundamental counting principle, again, that combinatorics part. Okay, 6 times 6 is 36. So that's where we get that number from. So then the probability of rolling a 9 or a 10 is 7 out of 36. Okay. All right, last one. Suppose you flip a coin 3 times. What is the probability that exactly 2 of the tosses result in heads? Okay, number of different ways you can do this. You can even make a tree diagram if you wanted to, or you can just list out the possible combinations. Okay, I'll actually just show you both. If you make a tree diagram, okay, on the first one you can either have heads or tails, and then you could have heads or tails, or heads and tails, depending on which event occurred. But you're tossing it 3 times. So again, you could have heads and tails as a result in any of these branches. Okay, so then just follow these branches down here. Okay, so first one was heads, heads, heads. Okay, so that's one possible outcome. Okay, let's say you flipped heads, heads, and then went to tails. Okay, that's another possible outcome. Okay, you could go heads, tails, and then heads. Heads, tails, tails. Okay, again, just following the branches down. You could go tails first and then get 2 heads. You could go tails, heads, tails. Tails, tails, heads. And tails, tails, tails. 3, 4, 5, 6, 7, 8. Okay, 8 possible outcomes from flipping the coin 3 times. And again, think fundamental counting principle here. 2 outcomes from the first flip, 2 outcomes from the second flip, 2 outcomes from the third flip. Okay, fundamental counting principle, multiply them together. So there's 8 possible outcomes when you flip a coin 3 times. And these are what those 8 different outcomes are. Okay, so we know that the probability of getting exactly 2 heads would be, well, that one works, and that one works. So it's 3 out of those 8. Okay, if this had instead said, like, at least, okay, well, then you would have to also consider the possibility of getting 2 heads or 3 heads. Okay, so then you would be adding like we did up here. All right.